Hello and welcome to another video tutorial series with your host JP Metcalf. Today we're going to go over rigorous orthorectification, and that is a process to be able to take satellite imagery and tie it into a source that has a higher accuracy as it pertains to on the ground, and update RPCs to where the image fits on the ground better, so that you can do things like change detection between images, or just have a higher accuracy image all around. If you want to serve it on a server and have people download that image and provide the accuracy metric. So to get started, I'm going to go to my browser and I'm at l3harrisgeospatial.com. And what I want to do is to find the tutorials is go to support and then self-help tools, and then little drop down shows tutorials. And once I'm there, we have step-by-step tutorials designed to help you become familiar with features and capabilities of ENVI, of course. And we have a list of the tutorials, which will bring us to PDFs. Then on the right-hand side, we have data for the ENVI tutorials. So what I'm going to do here, it looks like they are listed by date that they were put up. Rigorous Ortho is a little bit older one, so I'm going to start at the very end, going from 2013, and I'm going to look for something called RPC based rigorous ortho. Actually, no, let's do RPC orthorectification, and I'm going to open this up in a new tab so that I can have the PDF up here, and then zoom a little bit so everybody can see and follow along. And the way this works is I've never seen a lot of these tutorials, but I love to make videos of them just so users can have a little bit more information beyond just having a PDF. And sometimes you never know if you're doing it right. So you have me here with you to hold your hand and let you know what you're looking at, what to look for, things like that. And for the most part, I'll just go ahead and go over what the overview is. So we're going to use ground control points, an orthorectified reference image, and a digital elevation model to orthorectify an Orbu 3 scene that contains rational polynomial coefficients, RPCs. RPCs are something that are shipped with satellite imagery to be able to explain how that image is situated on the ground. And the reason that we're doing this is RPCs, they can get you close, but we want to refine the accuracy at some point. Especially if you're like we were talking about before, comparing image to image, like image to image. This is sort of like image to image registration, but we're saving that RPC information. So in this tutorial, we're going to learn two different methods for performing RPC orthorectification. The first one is to automatically generate GCPs from an orthophoto base layer, and then use those GCPs in the orthorectification workflow. This is an interactive approach that lets you assess the errors of individual GCPs, as well as the overall model accuracy. I think it's good to know. You might see something like in an error assessment that this image is within 2 meters of its actual location. And then the next step is to automatically generate GCPs and perform orthorectification in one step. So they sound very similar, but what's going to happen is first what we're going to do is we're going to generate GCPs. We're going to look at this error layer, which looks like an image, but with higher error in red, so we can see that visually. And then we're going to go through the steps of orthorectifying that image, and then the next one towards the end is just a fully automatic rectification tool that we don't have to change any of the GCPs or analyze their error. Let's say that we have a satellite, a satellite that has some ground station RPC refinement that is better than most, and we might be okay with some of the automated GCP generation. So as always with these tutorials, I'm going to talk about a little bit about the data. The files are available on that website that I was just at on the right hand side. So I'm looking at here, I have RPC Ortho. I have that downloaded already, but what you want to do is hover over this. It's coming from Amazon S3, and it'll be RPC underscore ortho.zip. And what we want to do with that is download it and then unzip the file. Go ahead and pause if you need to. But what's inside is going to be an orb view subset, panchromatic image of Coral Springs in Florida, acquired on 16 January 2006. The resolution is 1 meter per pixel, and that's from USGS. Then we're going to have a NAPE reference image .dat. That's what we're going to use to actually to say that this is the higher accuracy, and then we're going to try and match the accuracy with the orb view subset. That is from 7 August 2007, and it's NAPE with a GSD of 1 meter. GSD is just spatial resolution, and a tolerance of 6 meters to the true ground location. So horizontally, we're within 6 meters of the true ground location. That's from USGS. And then we also have a DEM that is from National Elevation Dataset, or NED, at 1.9 arc second resolution. And that is also, everything's from USGS, right? The reason we need this DEM is we need to be able to account for some of the terrain distortion. When a satellite image is collected, it doesn't really have any ground information of what the terrain is like on the ground. So we need to adjust for that. A little bit of background, talking about what RPC orthorectification is. The RPC model is a sensor model that maps the physical relationship between the 3D ground points and 2D image points. 2D image points being, upper left, upper right corner, and then the end of the image collection, you'll have the bottom, the end. And that maps to the ground somehow with Latin long. RPCs are not the same as a map projection, as we'll see when we look at the metadata. It's basically a combination of sample and line offsets. There's usually about 20 for each, and the very small numbers. Most modern high-resolution sensors, such as WorldView 3 and Pleiades, include pre-computed RPCs with their imagery. So this is something that just kind of is embedded in the image, or it can be a separate file. I know that Pleiades ships with RPC XML files and also DIM, which is another type of geospatial type way of explaining the image on the ground. The ENVI RPC orthorectification tool uses RPCs, of course, along with X, Y, and Z data from GCPs, elevation data, and high-resolution DEM to create an orthorectified image. Prior to ENVI version 5.3, you had to manually add GCPs to the RPC orthorectification workflow. Okay, so prior to ENVI 5.3, it takes a considerable amount of time to not only generate GCPs that they can come from any kind of GPS or GNSS sensor. You would have to go out in scene to be able to collect those, and usually takes a little bit of time to generate those. And then once you have those GCPs, then you can put them in your image. And then you would have to line up, where they are. When it could be corners of buildings or something that's easily recognizable in an image. We're working with 1 meter spatial resolution here, so corners might be kind of hard to find depending on how, what type of landscape that you collect GCPs over. But it sounds like we're doing a lot of automated work here, so we're not going to have what I like to call like ground control, right? Where you go out and collect it. It's a very expensive process, takes a while. So these will be automated tie points, is what I'm going to call them from here on out. So now you can automatically generate those GCPs or tie points from an orthorectified reference image in DEM. The reference image should have the same or slightly higher spatial resolution than the source imagery that we want to orthorectify. And we already talked that they're at the same GSD, 1 meter. For coverage within the United States, you can obtain digital reference images from the following sources. So you can get it from NAPE, which is the National Agriculture Imagery Program. And I'm not sure if that's US wide, but majority of the areas that I've seen where I wanted to get some kind of, let's call it base imagery, I've always been able to pull this. You can also go to US Geological Survey and find digital orthophoto quadrangles, DOQs. I remember hearing about those in my GIS undergrad. And there's also another one of DOQQ, which is a quarter quadrangle, so probably smaller size. USGS Survey high resolution ortho imagery, and you can also get this thing called controlled image base. Controlled image base is basically a package of ortho photos that has a little bit more information. Could be DEMs that go along with it. I've heard it more in the military aspect for obtaining controlled image base. So you can download the data from USGS, National Map and Download Platform, or Earth Explorer. Then you can use the seamless mosaic tool to create a mosaic of individual tiles. Try to choose a reference image that is close to the year and season of the input image. Automatic GCP generation is based on the image matching between the reference and source image. So the scene contents should be vastly different. Should not. If you pick them in close in year, and we'll look at our imagery, they're about a year and a half apart. You may want to just look at the imagery and see, oh, did anything really change? You know that, there's physical processes. There's, if you're of an urban scene or a suburban scene, that you might get, housing development, and then that area can look a lot different. Automatic GCP generation is more robust if the reference image and the input image have similar resolution. If the reference image has a much higher resolution than the input image, and the ratio is greater than 2.5, consider downsampling the reference image first. So what this means is, let's say we have UAV data at 3 centimeters. Because of the automatic tie point generation, we want to be able to kind of sort of apples to apples tie point generation, sort of say, where the pixels that we're looking at, we can find similarities in them. If you have that much higher spatial resolution at 3 centimeters, there might be pretty difficult to be able to find matches. I think if you zoom out, you might be able to get a little bit the ability to be able to tie them together. But in reference, if it's 2.5 for the ratio, so 2 times better resolution for the reference image, you might consider downsampling to 1 meter, in this case for the orb view. So we need a DEM, and that must cover the spatial extent of the input raster. If you do not have a DEM file available, you can always use the Global Multi-Resolution Terrain Elevation Data 2010, or GMTED, which is aptly named JPEG 2000, provided in the ENVI installation under the Harris/ENVI, whatever flavor ENVI you have, /data folder. So ENVI ships with a few data sets that you can use to be able to use as reference, basically. And a little bit of information about what GMTED. Since we're not using it today, I'm going to go ahead and skip this little part here. So once we do have a good quality reference image and DEM, you can begin RPC orthorectification. So let's get into it. So what are we on the 3rd page here? This is where it starts the actual tutorial. So the first thing we want to do is open the images. So I can either do that with file open, or there is a little icon that looks like a little folder. If I hit that, it's going to bring me into, well, I have it set to go to the tutorials file, the Windows Explorer. So I'm just kind of brought to it. But for you, you might have to navigate to the folder that you just downloaded and unzipped. And inside, you should have a similar layout to mine. And the first thing we want, the first thing we want to do is add all 3, actually. So what I'm going to do is I'm going to click DEM, DAT, and I'm going to hold my control key and grab that NAPE reference image and then the orb view subset. So I should be able to open all 3 at once. Or you can add them, individually if you'd like. Sometimes my control key doesn't work. And a little bit about the imagery, I can see that the nape and the orb view subset are reprojected. And the reason for that is that dem came in first, came into the layer manager. So the overall ENVI window is going to assume the coordinate system of that first layer. So it looks like we are in geographic lat long based on NAD 83. And then everything else is reprojected to it. And it looks like it reprojected well. So if I turn off orb view, which is this panchromatic black and white image, it looks like we have a nape image behind it that is, it covers it. So that's good. Here's the nape, which is true color. I'm going to open up my data manager just to make sure we don't have anything else like infrared, like a 4-band image. And it looks like we're just red, green, blue. If I turn off nape, what I expect to see is a DEM that covers the area. And if I look at the orb view, it fully covers it. So that's good. All right, so the DEM has some information in here. You know, if I wanted to look at this in different detail, I might change the color table for this black and white image, the DEM, into something like rainbow so I can see the higher areas. So it looks like the highways and some of these buildings here are higher in elevation than the rest. And it looks like the waterways are in this purple area here. And if I wanted to see the actual data values for the DEM, I'd bring up my cursor value tool. And I'm going to see that this is 1.4 meters in the water area. And then we get to about 3 meters in the suburban area, and then about 4 or 5 meters. Okay. In a little bit higher up. And then we have some overpasses that have that elevation getting up to about 8 meters. Okay. So I just want to see, that our DEM has elevation data in it. That's not always guaranteed. Sometimes it can be saved out as like a byte image. So I'm going to go back and take off this color table back to grayscale because it's a little bit easier to see. And I think we're good with this. If I look at nape and then I switch the two on and off, it looks like they match up pretty well. You can always zoom in and maybe look at a feature. And I think these match pretty well. And then what I'm going to do now is, so the idea here is that RPCs from the satellite give us enough information to get us close. And the whole point of this workflow is to get us closer or closest. So if I turn on orb view, I'm going to expect a little bit of horizontal air. So I'm going to look for something that I can see pretty concretely. And the trick here is I can't really see beyond my image, but if I turn on the transparency and look at the difference between the two, and I get it right about in the middle, say 50% transparency, and you see right here, it almost kind of looks like a stereo image that I have. We can measure this. I'm going to bring up the little measuring tool, and then below is the nape image. And if I measure from one corner of this building to the corner of the same building in the orb view image, we have a 13.5 meter air. Looks like a bias there of northeast or southwest, either one. So 13 meters, and we want to use that DEM to be able to match this image up with the nape. And as I look around, yeah, it looks kind of blurry. That's because it just doesn't match. And because of the relief in the image, I'm not sure there's not too much here. It's not mountainous. That air can be different in different areas, especially areas with higher relief. Okay, so we determined we have about a 13 meter offset between the orb view satellite image and the nape imagery. So if we right click on the orb view data set in the layer manager, we can view the metadata. So if I right click, come down to a little bit about the middle, there'll be a little view metadata option. And that's going to bring up, by default, it's going to have the raster information. So this says that it's about 52 megabytes on disk. It's ENVI type, which means it's a DAT. The number of columns and the number of rows is it's almost square, about 5,000 by 5,000. One band, that's panchromatic. BSQ is just the type of interleave and how it's saved. It's an unsigned integer image. And then we have an offset in the X and Y start. And then the sensor type is ORDView 3. So what we really want to look at is the RPC info. And it starts off with some offsets here. Line sample, height offset, it says 3. We have scales that are associated with those offsets. And then here we come down and we see those numbers that I was talking about. It should be about 20. Line numerator, and we get down to 20, and they're pretty small values. And then we get to the line denominator, should be 20 of those. Sample numerator, again, 20. Sample denominator, 20. So altogether we have 80 different values that are really trying to explain how this translates. We have tile offsets and geoid offset and a digital elevation model, but there's nothing associated with it. Now I assume that it would basically say this is what the RPC is tied with in this digital elevation model, but it looks like we don't have that information. And of course, we have the coordinate system, what it's in. It's a global WGS 1984 coordinate system. That's why it's reprojected. The DEM was NAD 83. We have extents. Spectral is not really going to tell us much, but if we were doing something like atmospheric correction, that this information would be good for us to know. Radiance to reflectance. And we have irradiance. So my spectral background would hone in on something like this: watts per steradian per meter squared per micron. Okay. Image parameters, we have that cloud cover doesn't really make sense. 999,000%. 999%. Sun azimuth is that's pretty much coming down from the south. Sun elevation, okay. Time, that was 2006. So January 16th. All right, keep that in mind, January 16th. And then I wonder if we have that metadata in our NAPE. Does that have a time? It says unknown. We'd have to always go back to when we pulled this from USGS to find out. But I know it's about, I think it's around June in 2007 is when that was collected. But, looking at the image right here, there's not that much of a change. So maybe it doesn't really matter what date it's from. Okay. We're going to zoom out until we see the extent of the combined layers, which we are. ORDView 3 panchromatic is on top. Remember, I have that transparency turned on. Now, it says we can increase the display area by detaching the layer manager, which I can do right up here. I have a pretty large screen. It's up to you, and get this off to the side. And the reason for that is if we're going to evaluate GCPs, that we're going to want the most screen real estate that we can, so we don't have to do a lot of panning, zooming, things of that nature, because we're going to want to look at the correlation of the image, the ORDView image with the NAPE image when we generate these GCPs. We haven't gotten there yet, though. I will leave this out here just in case. So now we're going to create GCPs. So in the toolbox, we're going to go to geometric correction. So on the right hand side, I already have it highlighted. I'm going to open up or expand geometric correction. And then it looks like I'm looking for generate GCPs from reference image. So right here. And then I'm going to double click. And a task comes up. It's going to ask us for the input raster, which is going to be our ORDView, our reference raster, which is the NAPE, and the input DEM, which is the DEM. So I'll do that real quick. So if you hit the little ellipsis, it's going to bring you to a data selection tool. And that's really the data that we have loaded in ENVI already. If you needed new data, at the very bottom, you can add additional files. and even connect to a remote data set. Remote data set would be great for if you have this high resolution imagery that you don't necessarily need to download, but uh, we want to use that as a reference. But we have that downloaded here. So for input raster or view, I'm gonna set that. And the reference raster, I'm gonna set as nape reference image. And the input dem is the DEM. And then do we want to say that the dem is height above ellipsoid? And I remember seeing values of like 1 to about 8, which kind of tells me that it's probably not. It's in Florida, so it's pretty close to the water. Usually I know in California it's about negative 34 meters for the height above ellipsoid for the ocean. So the NED dem contains orthometric heights, which are elevation values above mean sea level. Okay. So if we're above mean sea level, that explains the non-negative values. So let's see. Leave the default value of no. Okay. So we're good on that one. Keep the default value of 25 for a requested number of GCPs. We have that set. The search window size, tutorial doesn't say anything about that, but it is optional. And now we need to set the output GCP's file name. So if I hit the ellipsis, hopefully we're back in RPC Ortho. I don't really show anything because it's looking for .pts. So what I want to do is, it looks like it's up to us to name it whatever we want. So I'll name it automatic GCP. And what task are we in? We're in generation. Generation.pts. Okay. I might actually put in that we requested 25 as well. Then I'm going to hit save. And then that should show up as our path. So if I hit OK, what ENVI is going to do, it's going to write GCPs to the specified directory, but does not display them. So, but we're going to restore them later. Okay. So I'm going to click OK. And in the task, it says that we're generating tie points by cross correlation with orthorectification task. So as always, ENVI has a very robust help feature. So in that task, I could have hit that little blue question mark icon, and that would have brought up some information on what's actually happening. So if you think, all right, well, hey JP, we were talking about GCPs. Why is it talking about tie points? And what is cross correlation? Cross correlation is a method of determining let's call it the overlap of the images, and saying, all right, this point is probably that point in the other image. And then we're going to evaluate the error, right? And when I say tie points means that it's usually image to image, like generation of similarity. So if you think of image to image, that it may not necessarily have Latin long or a geospatial coordinate system associated with it. So you might just have, this point, tie point 1 is X and Y, which is pixel space for image 1, and then X and Y for the reference image. And this is how they go together. Think Photoshop, that you don't have a ground control system or coordinate system. And that's why I like to call these tie points. But in reality, what's going to happen is they do, the tie points do have a Latin long associated with each one, and we'll see that later. So now that we have GCPs, it didn't actually take that long to generate, but we have them generated, and now we're going to actually go into the RPC Orthorectification Workflow. You remember, we are on the first iteration of the Orthorectification Workflow, where it has that manual step of changing GCPs. So we want to go into geometric correction and then orthorectification folder. So I'm looking here, and I have orthorectification folder here. And it looks like I have several options. One is a wizard or a workflow. I say wizard because it has like a little magician's wand. And it looks like we actually want to use that one with the wand here. So double click that. And I should get a little wizard. and it wants to know what the input file is. That's the OrbView dataset. The DEM file, it defaults to that GMTED 2010 that ships with ENVI. That's just where it thinks the elevation data is. But what we want to do is change this to the DEM layer. And I'm actually clicking the layer. And now it says a geoid correction of negative 27 meters. So this sounds like if we're correcting for a geoid, that maybe RPC Orthorectification wants to have it in something else. So under the Advanced tab, we're not there yet. Hold on. Reading the notes. Under the Advanced tab, the geoid correction option is enabled by default. You should enable this when using DEM data containing orthometric heights. Okay, so that's what we have, right? If you disable this option, the horizontal accuracy value will increase significantly. And I think what they mean by increase, it's not increasing accuracy, it's the number is increasing, therefore the accuracy is lower. So we make sure we have this on. I don't think can I change this? Negative 27? Maybe I can. No, I can't change it. So that's automatically calculated. Now it says advanced tab, like we were talking about, this was written for ENVI 5.3, and this is ENVI 5.6.3 is what I'm on. So we don't have an advanced tab. But the RPC Orthorectification Workflow performs geoid correction by using the Earth Gravitational Model, EGM, from 1996, automatically determine the geoid offset. Okay. Let's hit the I believe button and hit next. And what that's going to do is clear out every layer that we had and then load in the layers that are only associated with these workflows. And we're looking at this OrbView image, which it's kind of cool. It looks like there's like a bunch of waterways everywhere. This is in Florida. And then we're met with the RPC refinement. So now what we have to do is import the GCPs. So it looks like I don't have a lot of information here. There's no horizontal accuracy. So the next thing I want to do is look at these icons down here. They're all grayed out except the one that says load. I'll hit load, and then I'm going to bring in the, I spelt it wrong, automatis. GCP generation 25 points. So it's a 2 kilobyte file. And you can also see here, I can either query for PTS or .shape. So shape files. We have PTS. It's going to bring all these in. And it says that we have 12 points. Now, remember we requested 25 GCPs, but through the error assessment, it found that only 12 are usable, and 12 is what we have. Okay. And there's a little bit of information here talking about that. During the GCP generation process, ENVI first creates tie points between the two images, then filters the tie points for radiometric and geometric quality. Radiometric being, on one hand, we have a panchromatic image, and then on the other hand, on the reference image, we have red, green, and blue. Now, if there was something wrong with the radiometry of the panchromatic image, it might have a hard time determining the correlation between the two images. So that's a consideration if you don't get any GCPs at all. The green check marks indicate that these GCPs are active and will be used to adjust the RPC model. These are called adjustment GCPs. Okay. So we have little green check marks for each GCP, and they're just automatically named. And I'm looking at the right-hand side, GCP properties. We have a map X and Y, a height, and it looks like this height is adjusted based on that geoid correction. Where it's located in the image. You remember our image is about 5,000 by 5,000. So I'm looking at GCP one. It looks like one's in a corner somewhere on the X. So either left or right. And then about 600 pixels in the Y direction. Okay. And its status is adjustment. And by default, all of these are adjustment. I can say independent. If I make them independent, it's not going to compute in the RPC orthorectification in the same way the other ones would. The actual adjustment GCPs. For now, they're all adjustment, right? Let's see. The horizontal accuracy value is the horizontal root mean square error, or RMSE. You might have seen that in meters. So we have a horizontal accuracy of 2.04 meters. So what that's saying is if we run the RPC refinement right now, we should expect a global adjustment to have a 2.04 meter accuracy update. So during the time of writing, it says 1.84 meters. So that just could be a difference of using different versions of ENVI. What we can do is view the errors. Here, we're going to assess the quality of GCPs and how they contribute to the overall accuracy of the orthorectification. Okay, so each one of these independently adjusts for this accuracy. So once we identify GCPs with larger errors, you can adjust them or delete them. Reevaluate the accuracy of orthorectification. That basically says if I delete GCP 1, this horizontal accuracy is going to change. Better or worse? Could change. So rather than give a mathematical definition of all the available error statistics, this tutorial will highlight the most important ones to evaluate, and will give you a more practical approach to understanding their meaning. For more details on error statistics, click Help in the lower left corner in the RPC refinement panel. When the ENVI Help displays, follow the link to Accuracy Assessment Background. Let's do that real quick. I'm going to click here for Help. I'm going to get a new little window. Apply ground control points. Okay. It talks about how to make them, what the icons mean. A little marker icon with a little do not use says that will not be used to adjust the RPC model. You might want to do that if maybe you do want to use it later. You just don't want to use them now. You can always kind of turn them off. Independent GCPs. A caution icon means that the difference between the image estimated ground coordinate and the GCP is greater than 3 times the RMSE in X or Y. See assessment background for details. That's where we go here, right? So if I click that, it's going to bring us further down in the help document. So the panel reports various error statistics, individual GCPs, and the entire RPC model. Okay, the table lists map coordinates, height above ellipsoid, image coordinates. We saw that. So the error in X and the error in Y, that makes sense. But then there's the error in Z, and that's going to be the height, and that's from the DEM. Then there's a magnitude, which is the square root of the X and Y. There is a link here that is a reference that's saying the Joint Research Center recommends that GCPs are at least 3 times or 5 times as recommended. More precise than the target specification for the orthorectified image. Okay, so you remember the NAPE image has a 6 meter error. So we want our GCPs to be at least 3 times, or recommended to be 5 times, more precise than 6. So 2 times would be 3 meters. We're sitting at 2 now. So if the target specification is 2.5 meters RMSE, the GCPs should have a relative accuracy of 0.8. Okay. So another thing is we don't have a target specification. If we had somebody that came to us and said, listen, I want you to do RPC orthorectification on this orb view data set, and I want it to be accurate to within less than a meter, that would be something that we shoot for, right? There's a lot of other information. You can take the time in here. I don't want to read through it. Close this. If I right click on the orb view data set and then select zoom to layer extent, okay. So I can right click it in the layer manager and say zoom to layer extent. I could have also done this. There is a button at the very top in the menu bar, zoom to full extent or F12. I actually rarely ever use the F functions, only because they're like double keyed. You know, sometimes you have to hold down the function key. But if you're that in that kind of production, F12 will get you there. Zoom out. Now we can view the air of each GCP visually by hitting this icon. It kind of looks like a little DEM. It is show air overlay. And what that should do is it looks like it's hugging the extents of our GCPs. So we have some in corners here. And it looks like they're kind of evenly distributed. Kind of hard to see in the video, probably. Little green crossbars. A transparent image overlay shows up in the scene, showing a color gradient of interpolated GCP airs. The darkest areas indicate GCPs with the least air, and bright red areas indicate GCPs with higher airs. So towards the top, in the north area, see that this GCP has a high air. And then we have a good, looks like a good match. Looks like I'm doing something right. And there's an example in the tutorial. The overlay is useful for quickly evaluating how GCP errors are distributed across the entire image. Use the zoom and pan in the main toolbar to explore. Okay. So when I zoom in, I can tell that this one has a lot of red around it. So let's see, can I click on it? Ooh. So when I just click that, it says it's GCP 13. So that makes me think that this is interactive. If I go to GCP 1, it's going to shoot to it. Okay. 2. So now it's showing a lot of problems. But you know, it's kind of weird. Did I do something wrong? Now it says that horizontal accuracy is 3.43. I might have moved it. 13? Did. And you know what? I didn't have 13. I just made a new one. So I'm going to delete that and we should go back to 2.04. Perfect. You got to be careful when you're clicking around things. You can either select a GCP or add a new one. So if I click on each GCP in the list and I look at the properties, I'm supposed to be looking at GCP 2 right now. And that's the area that has a lot of red. And if I scroll down on the properties, I should be able to see something in here that says the air magnitude is 4.55. The GCP is located at the top of the image and corresponds to the brightest. Yeah, it does. Here we go. In the RPC refinement panel, click Hide Air Overlay to turn off the air overlay. Do I want to? Hold on, let's explore real quick. I have another option here that says Show Air Vector. And I really kind of want to look with that, see what that looks like here. So now I have a little ellipse and then a little blue vector. And that directionality tells me something. That's probably, this is the horizontal air, right? In visual terms. But if I zoom in, I can check out the other ones. I have like a little vector for GCP3. And now that we're this far zoomed in, let me I want to actually see some pixels. So I can do that. There's this automatic interpolation that ENVI does. If you change the interpolation by right-clicking on the orb view data set and select nearest neighbor, we're so far zoomed in, we'll actually see each pixel. The interpolation is just for, to make it look pretty. I like to see the pixels though. So if I'm looking at this right, I'm assuming that the cross correlation GCP automation was probably trying to hone in on this corner of this building. Here are some on the edges. And of course I can look at the magnitude. This is almost 2 for GCP 9. 10, a little bit better. GCP 11 is apparently right on point. GCP 12 is doing pretty good. Okay. So to correct errors, remember we also need to turn off the error overlay. We'll go back out to full extent. Notice that we're also not showing the name. If more accurate geolocation information is available for a given GCP, that's where I was saying where you could go out and have either a total station or a GPS tripod where you would collect GPS measurements over time and then correct those and have a very precise measurement, right? You can get down to centimeters, sometimes millimeters. And then you can actually input those. It'd be a little bit harder to utilize something like with a millimeter accuracy when you have a meter pixel, and we can't really do anything about this right now. So everything within that is like basically subpixel. So we can make edits in X and Y values in the GCP properties table. So if we had the lat long, we could just add those in. However, in most cases, it's more practical to interactively move the GCP location in the image display, then evaluate its error statistics, or delete a GCP if moving its location does not improve the error statistics. Okay. I'm going to say right now, it says that it's practical to interactively move the GCP location, and then, like, if you see an accuracy get better, that we should just use that. I'm not too sure about that. What I would want to do is evaluate the actual nape image to see what the cross correlation actually picked up on. Because if you look at, we zoom in and look at the GCPs, one would hope that this is a parking lot that it's picking up. Hopefully, it's not a shadow, right? And if I just start interactively moving it around, it's I'm not doing us any favors by not actually placing it where it actually is, right? So what we're going to do is GCP2 has a high error magnitude of 4.55, and it looks like we're over in maybe like an apartment building. And it's in what I think is the shadow. What we want to do, according to the tutorial, we're just going to delete this. So this big red button is delete GCP. Be careful not to hit the delete all GCPs icon. So if I delete that, what should happen is the horizontal accuracy should improve, and that this 4.55 error magnitude is really contributing to this 2 meters. So if I click delete, we update the error, and that is 1.45 now. So now, if we look at GCP1, that error magnitude is in the parking lot. It's saying that if we move this marker a few pixels to the southeast, our accuracy should improve. Okay. So I have my select tool on. And if you look at, I'm going to zoom in all the way where the tutorial says, and it says if we put it right around here, that our accuracy should improve. So now we just went from 1.5 to about 1.13. Can I get it better? Wow. Maybe it's this pixel. I'm moving it within a pixel, so I'm not very confident that that's really actually. I'm going to continue this process until the horizontal accuracy is less than 1 meter. Okay. So let's say that I'm going to move this way out and see what that does. All right. So I'm going to settle on this pixel right here. If I go to 3, let's zoom out and see what that looks like. And that one looks like it's picking up on a sidewalk. And that error magnitude is 0.86. So if I move it around, getting worse. Get better. Oh, a little bit. Here we go. 1.07. Let's leave that one there. Let's go to 4. Zoom out. This is be a driveway. But I'm just gonna like move it around within a few pixels. Remember I said I don't really recommend this. 0.28, 1.08, 1.04. Okay, so this pixel is doing pretty good. Did I find a 1.03 in there? 1.02. So let's put it right there. GCP 5 has an error magnitude of 1.7. Out. Again, we're in like a apartment complex. I'm gonna guess, and that made it worse. 0.92, 0.90, way in. I'm just gonna check some adjacent pixels, see if that's 5, 5. 0.84. Check one down here. Let's settle on this pixel up here. 0.84. CP6 appears to be house. It looks like the corner of the house. So we are looking at a magnitude of 1.45. That adjusts. That got worse. 0.72 better. 0.69. Not getting worse. What about here? 0.70. 0.68. I'll say that's fine. The error magnitude is 0.05. That's doing pretty good. Another house. And we're looking at an error magnitude of 0.6. See if I can't get that down. No, got worse. 0.51. Okay. CP8. That looks like to be a corner of a house. We have a GCP8 has an error magnitude of 0.68. So can I improve that just by 0.55? Go to 9. Point or 1.15. That got better. Magnitude is pretty low. 0.3. Go to 10. I improve this a little bit. So now our horizontal accuracy is all the way down to 0.47, a half a meter. I'm not sure if I do anything after this, it's going to be real. 0.49, 0.2. Lastly, here's GCP 12. 12 has an error magnitude of 0.47. I get it better than that. 0.10. What if I just my hands off the keyboard at that point? 0.06. Okay. All right. So we're all the way down to 0.40. And that's doing pretty good. Where did the tutorial get? We have some information here. Elevation data significantly improves the accuracy of the RPC orthorectification, so that is why a digital elevation model is required for input. The RPC orthorectification workflow uses elevation data in conjunction with geolocation data to compute an RPC solution. We're doing all this on the fly, computing the horizontal accuracy, which is good. So we're going to select the statistics tab and look at the RMSE Z value. Okay. Real quick, I want to see what's in advanced. Advanced is UTM zone 17. Okay. That's what the output will be. You remember we have like global coordinate systems for these products. So GCP statistics says, all right, all and then adjustment GCPs, which should be the same because we don't have, there we go, number of GCPs, none, no independent. So all should just be the same thing. We have an RMS-EZ value of 0.17, so 17 centimeters. We're also seeing these additional metrics as CE 95. That's the circular air within 95% confidence level. So you see the circular and the horizontal, and that's going to be what we saw with that vector overlay. And then vertical accuracy, we have linear. It's only linear because it's one direction. Okay, so we have 11 GCPs. I thought we had 12. Oh, we got rid of one, right? GCP 2. So we're all well within a meter, whether it's RMSE, R, X, Y, circular. Okay. And the air overlay threshold is 3 times the RMSE. So that makes it sound like if we put on that overlay, should we not, if we're like less than 3 times, we not see any red at all? So this one's what, the worst one? GCP 7. Oh, and that's why we turn the overlay off so we don't have to 6.9. Oh, we're getting better. Okay, I think this is this is as good as I want for a tutorial. So we're down in a horizontal accuracy of 0.35. Okay. RMS-EZ value is the root mean square of the air Z values for the entire image. This is all dependent on the height. It reports the vertical accuracy of the entire RPC model. LE 95 is the difference in meters between the GCP measured elevation and the DEM elevation, using the calculated geoid offset at the 95% confidence level. So LE is linear air. So what this is saying is, and what I'm getting from this is we got to really make sure when we add an elevation model that we are making sure that the geoid correction is, if we're doing it, if it's correct. So we can save the GCPs to a file once we're satisfied with the quality of the GCPs. I'm going to go back to GCPs tab, and then I should see something like this archaic floppy disk. I say archaic because I think we haven't had floppy disks for well over 20 years, maybe around that. But we still use it for saving output file name. I'm going to put in, instead of automatic GCP generation, I'm going to put in adjusted or manually. I'll spell adjusted right. Adjusted GCP. And instead of 25, we have 11. So that's going to save that. You really do want to save that probably over time, a few times, because that manual method can be long, especially if you have a large image. This is a subset, and normally satellite images can be quite large in area. Now that we have reduced the individual GCP errors and the overall model error, you can preview the orthorectification in a limited area before orthorectifying the image. Okay. So it doesn't say like preview it, but what I think we can do is, can we hit this preview button? And what it should do is it show where it moves. So you remember I found between this building and that building, but it was up in a different area. There was about a 13-meter air. So this is showing where it's going to be after the adjustment. And again, I have this interpolation that makes it a little bit different. I can actually turn on blend. So the little blend video will show you where it's going. Okay. And I can have flicker, that'll flicker back and forth. So what we're doing is we're moving it. Okay. I can turn the border off. Okay. Let's turn the preview off at that point. So we have the GCP saved. We looked at the statistics, and when you do this kind of work, it's good to have a background in air, right? And there's a lot that goes into it. It's a lot of statistical ideas and concepts that go into this. Some of them can be pretty basic, you know. What we saw was just a simple square root. Now what we want to do is notice that the output coordinate system for the orthorectified result will be UTM zone 17 by default. I like to work in UTM zones. They have an offset, so it's really easy to type in the coordinates because it'll be like, let's say 500,000, and then for the X and the Y might be like 4 million or something like that. Those are easy to like copy and paste instead of adding the little, trying to get the little decimals, or, you know, do I need to use spaces for lat long, or do I actually need to put that little character in there that you would never find on a keyboard? So they're all positive values, which I like. We're going to go to the export tab and choose a directory where to create the image. And for output file, I can do TIFF or ENVI. If I leave it ENVI, it'll be a DAT file. And it looks like the output file, it already just gave it a name. I'll leave it at that. And it looks like where it's going is, I'm fine with that. Enable the export orthorectification report option. I'll do that. That looks like it's automatically named as well. And that is a .txt. That looks good. This report will list the source files used, the adjustment and the independent GCPs, the offset in geoid, air statistics, and output settings. So if you're doing this in like a production type environment and you're going to be disseminating this imagery, this is where that air report, no, I wouldn't call it air report. This would be the adjustment report that you'd want to include with the image. Just so the people ingesting the imagery knew where, you know, kind of like the pedigree of what's been done to this image. If we click finish, we're going to generate the orthorectified image. And within this little workflow, we have a, you know, where it's at in its process. Now we're exporting the results, and we should be done. All right, the layer manager is trying to add things. There we go. Now I'm gonna click that layer manager. It's a little foreign to me having it floating around. I'm gonna get it back in there. So now we have the new image, and if I bring out the layer manager, I can see that we have ortho view or view subset, and then or view subset RPC ortho. It will have some black background pixels along the edges because of the reprojection that took place, and that is correct. If I view at the very top left here, this should be no data. If I click this off, this is the new image. If I click this off, it looks like we don't have that no data here. And all right, let's look at this real quick. In the layer manager, toggle the orthorectified image on and off to compare it. Okay, let's do this on steroids. This is the original image. And just looking at the edge here, the roads doesn't line up. Do not line up. But if I turn on this new image, And it's kind of hard to tell up here because of that black bar, right? I could always, let's do this. It's not going to be in the instructions. But if I find out that this is 0, okay, what I'm going to do is in the metadata and in the edit metadata, I'm going to tell it that no data is 0, and then it won't show that. Okay, so we have spatial. It's trying to read the header right now. We have spatial, spectral, display, other, and custom. So what I want to do is add one. That should be data ignore value. That go in custom. Oh, it hasn't been yet. So at the very bottom, I have a new little, entry called data ignore value. I'm just going to say 0. And as soon as I hit OK, what should happen is that black bar should go away. And now, in this area in particular, I can actually see that it lines up. That's just for that area, though. Even better yet, here's a road, water lane. Let's see, that's just the corners. Here's another cool thing I can do. If I turn on the transparency of the data set, I shouldn't really see anything move. You remember the previous image that we had, and I can always bring it up, made it look like it was stereo. So if I add the transparency here, now it looks, this is what it looks like when you try to look at stereo pair imagery. It's like fuzzy. They just have different look angles, right? So this is how much we moved the image. And now we have a more accurate satellite image. Okay. Now we're going to forego all the manual process, and we're going to use RPC orthorectification using the reference image tool. All right, so I'm going to get rid of some of this stuff here. Let me get rid of this new image. Remember, we have it saved. We could always bring it back. And what else do I want to get rid of? I'll get rid of this overview one here. Just in the layer manager. And the DEM. We just have the nape. So the RPC orthorectification using reference image tool quickly orthorectifies the RPC image. It automatically generates GCPs using the reference image in the DEM. The tool is useful when you want a more automated approach to generating GCPs without checking their RMSE values. To do that, follow these steps. Okay. Display the nape. We did. We're going to compare this orthorectified image to the reference image later. Interesting. In the toolbox, expand geometric correction and orthorectification. Did that. And double click RPC orthorectification using reference image. Let me expand my toolbox a little bit so we can see the actual titles of these. So we have build RPCs. We have RPC orthorectification using ESM. That's for stereo. And then we have RPC orthorectification using reference image. That's the one that we want. So this task looks very similar to what we used before, but it combines the generate GCP and perform RPC orthorectification into one task. So what I want to do here is I'm going to add the input raster is going to be ORView subset, not the orthorectified one that we just made. The input reference is always going to be the nape, and the DEM is going to be the input DEM. Height above ellipsoid is no. And then for the requested number of GCPs, remember we only got 12 from the last one, and GCP 2 was bad, and we just got rid of it. We're going to over ask. We're going to request 40. And then we're going to come down here, output coordinate system. Apparently we leave that blank. I could put UTM zone 17, but maybe it defaults to it. We could change the output pixel size to be, it should be a meter, right? And we're going to leave the default value of bilinear for resampling. You know what? I'm going to change it to near. I'm going to go off track and change it to resampling for nearest neighbor. I like nearest neighbor. It doesn't really mess with the pixel values. It just translates them, which is very useful for hyperspectral imaging. Hyperspectral imaging. You don't want to do, when you're doing rectification with hyperspectral data, you don't want the spectral values to change, because when you use anything other than nearest neighbor, it's going to change it in some way. Leave the default value of 10 for grid spacing. Okay. We're going to enter an output for the orthorectified raster, and that is going to be, let's see. We have orb view subset RPC ortho. And I'm just going to make a new one called automated. Output GCPs is going to be automated. Automated GCP generation. Enable the display result option. What this is going to do, it's once it's done, it's just going to pop in the newly orthorectified image. All right, so I'm going to go off track here real quick. We're almost done. And you remember there's help down here, but we also have this additional little option called open in modeler. And what that does, as soon as I fill all this stuff out, actually, it doesn't really rely on having all these filled out, because once I open it in modeler, it's just going to have generic input parameters, which is going to ask us what we want to use. So ENVI modeler is a graphical user interface for programming, like visual programming. So this task, like I said, it's 2 tasks rolled into one, and that's generate GCPs from reference image and RPC orthorectification. And I can tell just from the way it's set up that the input parameters is going to ask for some information, and then RPC orthorectification is going to ask for some too. So if I click on the little, I call it a hamburger, it has input raster, DEM, GCPs, all the things that you would want to be able to put into this, right? RPC orthorectification is going to want to know the GCPs, and that's coming from generate. No offset. Okay. So see how this connection, this is the output from generate GCPs goes into RPC orthorectification, which makes sense. So if I hit run on this, this task is going to look just like this. I've put them right next to each other. They should be very, very similar. Okay. So I can always fill that out. This is useful for when you have a lot of imagery to orthorectify with the same type of parameters, right? If you're using you probably don't want to use the same D. It depends if you have a bunch of satellite imagery over the same area. But this is a way to automate some of these processes. You can even add things in here. If we had some kind of problem, remember that in the help file, it was talking about checking the radiometry of the image. If your image cannot be like interpreted by a computer, it needs, something else in there, you might want to do radiometric calibration first. And I might like sever this, right? This relationship and the input raster. There we go. Add new input calibration type. Things like this. And then I'd want the radiometric calibration, which would be, let's say, depending on what the orb view was in the beginning, it could be raw or radiance. And then I might feed that newly generated radiometric image into GCPs. That might provide a better result. This is a tangent. I'm going to close this. Maybe I'll do a whole video on that. What I can do here is just hit OK. You're going to see the same tasks go by. Generate tie points. You can repeat the process and experiment with different values for a requested number of GCPs. So that's where I brought up the modeler, because you can just change one value and just say, all right, run it again. Instead of going through that wizard or a workflow, and you have to keep adding in the, what you want to name it and things like that. So with display option checked, as soon as this is done, the new ortho-rectified image should just pop into the display and we should be able to check them. And then before we get out of here, I want to check out what the difference between this image and the one where we did manual CP placement. So we have that black bar again. If I look somewhere where there's no black bar, I would expect for these to line up. Okay. It looks like 40 is doing pretty well, right? Now let's bring in, let's see, we still have it here. Load that data. And what I expect is that if I do something like transparency, I shouldn't even see the difference. They're basically the same image. I didn't see an error report though. So what I should do is check. We have an error report for the automated one. Doesn't look like it. Let's check out the one that we did manually. Oh, that's good info. Here's the report. The source image is this. The DEM image is this. Geoid comes from built-in ENVI data. Okay. The GCP file name was saved as a shape. This is where the export image, the pixel size is 1. Here are the statistics, and we have all less than a meter. And then we have values for adjusted X and adjusted Y for each GCP. So that's kind of good to know. Like when the tie points came out the first time, they're like, we think it's this lat long. But after you manually did everything and adjusted it, this is what the lat long is. So it's good to know. You can use those in maybe a different RPC orthorectification process. All right, that looks good. We went over RPC orthorectification with an orb view data set and a DEM and a reference image from NAPE that was a meter GSD for both the NAPE and the orb view image. We did it manually with creating in manually adjusting GCPs and then doing the orthorectification task. And then the second part of this tutorial was to do everything automated, but we bumped up the requested number of GCPs to about 40. And I look forward to seeing you at the next tutorial. Thanks.